So now we're going to take a look at the algebra behind what it takes to produce the graphs that you saw in the previous examples. I'm going to do 4 separate graphs, each of them having different aspects that occur in rational functions. This first example is just the basics, okay? And so a couple of things to remember about rational equations, expressions, and graphs is that there is a parentheses on the numerator and the denominator. Very important to understand things like these x's can't cancel because you can't cancel through a parentheses. You'd have to cancel the entire thing at once, and clearly those don't cancel because they're not the same. So how would we cancel out an expression? We would have to factor. So why is that important? Nothing factors, nothing cancels, so we have no whole. Always find wholes first. The whole is the most important thing in the problem because once the whole is found, the entire problem changes. We'll see that in the next example. So if you go back and look at the notes for how to find a vertical asymptote, it said in the notes that you should set the denominator equal to 0 and solve. So if I solved this, I would just add 2 to both sides. And so my vertical asymptote is at x equals 2. Now, that may feel the same as a domain restriction, and it is similar. A domain restriction is to set the denominator not equal to 0 and solve, which will give you x does not equal 2, but that does not equal to 2 goes into the domain. The asymptote is at x equals 2, so we have an equal sign. The horizontal asymptote is found, okay, by looking at the degrees. You could divide the denominator into the numerator, and we have to do that for slants, but the shortcut works like this. If the degree of the numerator and the degree of the denominator is the same, then you divide the coefficients that are in front of that term. So in this case, it would be y is equal to 1 divided by 1, which would be y is equal to 1. The x-intercept of any problem is to set f of x equal to 0 and solve. So we'll do that, and then we'll use the solving techniques we learned in this chapter. So the solving techniques we learned to solve an equation or an inequality would be to multiply by the LCD, which in this case there's only 1, so x minus 2. And I want you to see what happens. It cancels here, but here it gets multiplied by 0, so it goes to 0 as well. So some teachers will tell their kids the shortcut for x-intercepts is to set the numerator equal to 0. Now that can get confusing because of the fact that setting denominators equal to 0 are asymptotes and things like that. So if you just want to set the problem equal to 0 and then immediately cancel out the denominator, that's fine. Now one really important thing to understand is if I leave this x-intercept like this, it looks like an asymptote. I have to come back and rewrite this as a point, right? It is the point 1, 0. Do not leave it like this. It looks like an asymptote or a line. The y-intercept is to plug 0 into f. So I'm going to plug 0 into the x's of f and reduce. And that will give me 1/2. Again, I can't leave it like this. I have to write it as a point 0, 1/2. All right, so now I'm going to take this information and see if I can determine the domain. The domain is always simply whatever the graph is. It's all real numbers except whole, or this number. So that's doable without a graph. The range and the in behavior usually require the graph to determine. So I usually wait on those, but it's important to prepare you for the idea that this is simply everything but these 2 items. And as you can see, that's how that domain restriction ties in. All right, so let's now graph what we have. We have an asymptote at 2. We have a vertical asymptote at x equals 2. We have a horizontal asymptote at y equals 1. So y equals 1 is right there. I'll go ahead and label those for us. So y equals 1 is right there, and x equals 2 is right there. And we have an x-intercept at 1, 0. So let's graph that x-intercept at 1, 0. And we have a y-intercept at 0, 1/2, 0, 1/2, so I'll put a dot there. And the bottom line is we just don't quite have enough to graph yet. So what most teachers do is they have the students make a chart. The chart is an organizational tool. So we're going to put what we know centered around always the vertical asymptote. So this D and E here, that is talking about the fact that if I put my vertical asymptote with x equals 2, the equation, the function doesn't have a value. So centralize your chart at the vertical asymptote. And in fact, you can think of the vertical asymptote and the horizontal asymptote as axes that have been shifted. There is a way to do that in a later class to talk about this graph being translated. So let's fill in what we know. So if I go smaller than this, I would have 1, -1, sorry, -0 and then -1. Just you go integer values. And then if I go integer values above 2, I would have 3, 4, and 5. If we already know what 1 is the x-intercept, so that's 1, 0. This is the point that I have right here. And 0 is a half, so I already know that value. So now I'm going to figure out these other missing pieces by plugging them in one at a time into here. So the function is x minus 1, so I would have -1 minus 1 over -1 minus 2. And that will come out to -2 over -3, or 2/3. And so now I could go up here and graph a point and show, oh, it's going towards this asymptote because at -1 it's higher. It's at 2/3, which is 0.6, right about there. You could, of course, use a calculator if you need to. So if I put 3 in, I would have 3 minus 1 over 3 minus 2. I got those values from simply plugging 3 in here. So 3 minus 1 is 2, 3 minus 2 is 1, so this would just be 2. All right, so at 4, I would have 4 minus 1 over 4 minus 2. Again, I'm just using the function with 4's in it. 4 minus 1 is 3, 4 minus 2 is 2, so that would be 3 halves, or 1.5. And now if I use 5, it would be 5 minus 1 over 5 minus 2. So that would be 4 over 3, or about 1.3. So now I will go and graph those and get the other side of the curve. Remember, this curve is already pretty evident, just as long as you follow the guidelines, but the other curve needs to be determined as well, and there was nothing to help us out beneficially with points from the problem, so I had to go find them. So 3, 2, and then 4, 1.5, and then 5, 1.3. So now you can see a nice curve, and you will trace the asymptotes, go through your 3 points. Yes, you need 3 points before the vertical and 3 points after the vertical. So there are my 3 points before the vertical, and here are my 3 points after the vertical asymptote to show a nice, clear, well-defined graph. So now it's pretty evident that the range is everything except the horizontal asymptote. Remember, beep, stop, beep. So you could use, again, you could use interval notation, but we're going to use set builder to prep us for trigonometry. So x is a real number. Sorry, that should be a y because we're talking about range. It's a common mistake, especially after you've done a problem and it's taken a little while. So range is y is all real numbers except y cannot equal 1 because that's where this asymptote is. The end behavior, if you label this arrow, negative infinity goes to 1, and at infinity it goes to 1. And again, it's simply this value. So if you want to just know that, it's really important on a test. It's sure to save you a lot of time. Can you imagine making a graph to determine the end behavior when the end behavior is always, for every rational function, going to be the horizontal asymptote? The only time you would ever have to worry about it not being the horizontal asymptote is if there is a slant asymptote. So there's your basic example. It's a lot of information. So take your time and learn one thing at a time and learn it well. And if you have a question, focus on the parts you know and can do, rather than giving up on the whole problem because you don't understand, for instance, one portion of it.